Hi, everyone. So today I'm going to talk about our work on using network slicing to provide service assurance for 5G applications. This is joint work with Mani and Victor at Microsoft Azure for Operators. You've probably noticed over time that you've been able to do a lot more from your mobile devices. That's in part because cellular technology, which is currently at the 5th generation, has been evolving to support a wide variety of apps, including video conferencing, IoT, virtual reality, cloud gaming, and vehicular communications. An important change is that these apps have heterogeneous requirements from the network. For instance, a good Zoom call requires at least 2 megabits per second of throughput and at most 150 milliseconds of latency. By contrast, a virtual reality headset communicating with a cloud server doing rendering requires more bandwidth and has more stringent latency constraints. And then IoT traffic may not have hard constraints on throughput or latency, but may instead care that the sensor doesn't consume more than, say, 100 milliwatts of power. Older generations of cellular technology were designed for more homogeneous broadband applications, not ones whose network demands vary so significantly. So in this work, we asked the following question. Can we reliably provision network connectivity to mobile applications? Now, when we ask for reliable network performance, we want this at all stages in the network. Let me illustrate the network topology for a mobile app. We have content that's hosted at an application server. This content traverses the wide area internet, eventually reaching the gateway to an operator's network. This could be a carrier like AT&T or Verizon. And then the operator's core network forwards the traffic to a radio access network nearest the end user device. And the radio access network then delivers the content to the application over a wireless medium. In this work, we focus on the radio access network. It's the last mile link to the end application. And it's been well documented that this link is often the bottleneck link for cellular applications. There are two reasons for this. First, the RAN uses a wireless medium, so the capacity or bandwidth is inherently variable. Second, devices are mobile, so the channel quality that they experience will vary based on their locations. If we can make connectivity more reliable for apps on this last mile link, they're likely to be more reliable overall. The next paper in this session actually looks at providing differentiated connectivity as well, but for the optical backbone network. What do we mean by provision network connectivity to mobile apps? Imagine you have a few apps that we want to connect to a RAN. The operator can schedule these time frequency units known as resource blocks to apps. In this grid, the x-axis represents time slots and the y-axis represents frequency or bandwidth. An app developer or user should be able to tell the operator what kind of connectivity they would like from the network. Let's assume this is formalized as a service level agreement where apps specify a minimum throughput and a worst case latency. What we want the operator to do is to allocate these radio resources in a way that fulfills the requested SLAs. So how can we realize this in 5G? The 5G standards formalize a way to create virtualized networks through an abstraction called network slicing. An operator can partition the radio resource grid into slices, assign apps to slices, and then schedule resources locally within each slice. The important thing is that the slices don't have to be static. Operators can tune how much bandwidth they want to give to each slice over time, and then also add or remove users from slices as they wish. In cellular scheduling, there have been two approaches to providing service assurance loosely. The first class of methods are priority-based schedulers. These are typical base station schedulers that have been modified slightly to include weights for each app that control how frequently apps get scheduled. But they end up having little bearing on the metrics that apps care about, like throughput or latency. The other class of methods do what we call slice-level service assurance. In these methods, operators define SLAs for a slice, like aggregate throughput for all apps, and then allocate bandwidth to the slice to fulfill that SLA. Neither of these approaches are suitable for app-level service assurance, which is our goal. Let me illustrate why slice-level service assurance falls short. Consider this example with two slices. We have a slice serving two apps doing VR rendering offloads, each requiring 8 megabits per second of throughput and 60 milliseconds of latency in the worst case. The second slice serves a video download app. It's bandwidth intensive, but not very latency sensitive. This time series chart plots the channel quality experienced by each app in the experiment. We measure this as a signal-to-noise ratio where higher means better channel. Notice that the two VR rendering apps shown in turquoise and orange have vastly different channels. Now let's run a slice-level service assurance method that optimizes the VR rendering slice to receive 8 megabits per second of throughput on average. Here's the throughput over time achieved by each app in this slice. The horizontal purple line shows the 8 megabit per second SLA value. Notice that this method only fulfills the SLA for app 2, the orange app, because its channel quality is superior. By contrast, though, it fails to deliver for app 1, whose channel quality is inferior. But on average, it achieves around 8 megabits per second of throughput. The problem here is that optimizing for a slice in aggregate ignores the network dynamics of each app, and it's the same story for latency. What we'd like instead is something like this. Notice that this method meets the throughput and latency requirements much better for each app, even though their channels are vastly different. So we introduce Zypper. It's a system that uses the same abstraction of RAN slicing to deliver app-level service assurance. Let me first walk through the architecture. Let's say we have a few apps that want to join the network. These apps specify their SLAs, and first an admission controller decides whether or not to admit the app. If admitted, the operator assigns the app to a slice, and then the bandwidth optimizer in a real-time loop dynamically tunes the slice bandwidths to fulfill SLAs. The computed bandwidths are fed into each slice's max scheduler that decides how to allocate resources among the users given the bandwidth. And then the max schedules are fed to the physical layer that computes the wireless signal to send over the air. Finally, the measured SNR is sent back to the bandwidth optimizer. Now, most of this architecture consists of standard components, from admission control to bandwidth optimization to separate MAC and PHY modules for each slice. To build Zypper, we're going to rethink two key components, the bandwidth optimizer and the admission controller. Now, with this overview of how we might realize app-level SLAs through network slicing, there are two key challenges that we need to address. The first is the search space complexity. In many ways, the architecture I described to you on the previous slide is similar to a system that does slice-level service assurance. But the bandwidth optimizer for app-level service assurance will have a much richer state space, including the measured throughput, latencies, and channel conditions of each application in the slice. Traversing this expansive search space to find suitable bandwidth allocations can be expensive. And the paper goes into this challenge in more detail. The second challenge relates to admission control. App-level SLAs make service assurance more stringent because we need to support all of the apps and each of their constraints. We want a fine-grained way of knowing whether the RAN has resources available to support an incoming app. Let me describe that in more detail. This diagram illustrates how an admission controller works. First, given an incoming app's SLAs, we ask the following question. For a given contract duration, can the RAN fulfill the SLAs for the incoming app without compromising on commitments that it's made to existing apps? If there's no bandwidth available, then the operator rejects the app. If there's available capacity, then the operator decides to admit or reject depending on its policy. The specific admission control policy can depend on a wide variety of objectives like slice monetization preferences, operational costs, fairness, and energy constraints. The specific policy is not the focus of our work. We leave that to the operator. Instead, we're going to focus on a primitive to determine if Zypper has the capacity to accommodate an incoming app. A common approach to determine RAN resource availability is to translate the SLA into a measure of resource blocks required to accommodate that new requirement. Let's see this with an example. Let's say you have a RAN serving two apps with this resource schedule shown here. Now we have a new app with a throughput SLA of 1 resource block per slot and a latency of 5 slots. Simply translating the throughput SLA for app 3 to a bandwidth requirement would result in a schedule like this. Notice that it requires adding an extra resource block of bandwidth to the slice. What we want is a schedule more like this. Notice that we can now accommodate app 3 without any additional bandwidth. SLAs are two-dimensional because they depend on throughput and latency, and then a slice could have complicated max schedulers. And the behavior of that scheduler could depend on the status of the app queues and the channel conditions of the different users. So simply mapping SLAs to bandwidth through an analytical model doesn't capture these intricacies. Back to Zypper. I'm going to talk about the bandwidth optimizer first and then get to the admission controller. Remember that the goal of this bandwidth optimizer is to determine how much bandwidth to allocate to each slice given the SLAs of each app that has been admitted to the network. We're going to use model predictive control. It's a popular framework used for many real-world control problems, where the key idea is to decouple a controller which solves an optimization problem from a predictor which explicitly models uncertainty in the environment. The uncertainty in the environment could come from the traffic patterns of the applications and from the wireless channel. Given predictions from a model and the current state of the system, the controller then selects a sequence of slice bandwidths. The RAN allocates the computed bandwidths, and then the measured throughputs and latencies are tracked over time as part of the state. And then the measured SNR can be used to update the model. To determine a suitable slice bandwidth, the controller conducts an iterative search over candidate bandwidths invoking in each step the slice's max scheduler to evaluate candidate schedules. Wireless channel prediction is fundamentally challenging. We find that we can get by with a modest prediction error of around 2 dB without impacting the performance of Zypper. I'm going to skip the details for that in the interest of time, but you can check out the paper if you're interested. Now I'm going to talk a bit about the bandwidth optimizer. So what we want to do is to compute a set of bandwidths b sub I for each slice I, such that every app SLA is fulfilled, and the total bandwidth used is minimized. And as I mentioned earlier, we can recompute these bandwidth allocations frequently, say every 50 milliseconds. Now, how do we compute the minimal bandwidth for each slice? The challenge is that we want the bandwidth to result in a resource schedule for the slice that complies with all SLAs. Now, it's hard to derive an analytical mapping for this relationship. So instead, we're going to approach this with an iterative search algorithm where we invoke the slice's max scheduler as a building block and then evaluate resulting schedules to see if the SLAs are fulfilled. Now, searching through all candidate bandwidths is prohibitive. So how can we prune the search space? Our insight is that throughput and latency vary monotonically with slice bandwidth. Consider this example of 2 apps with different packet sizes, and let's consider a round-robin scheduler. So this is what the schedule would look like. Notice that app 1's per packet latency is 3 slots. And now let's say we add some bandwidth, like 2 more resource blocks. Now app 1's per packet latency is 1 slot. So therefore, per packet latency is a monotonically decreasing function of slice bandwidth. And we also show in the paper that app throughput is monotonically increasing with slice bandwidth. And we use these 2 insights to build an algorithm to prune the search space efficiently. OK, so we've talked about the bandwidth optimizer and how we can deal with channel forecasting. And so now let me talk about estimating resource availability for admission control. A strawman approach is to say, how about before admitting the app, let's drop it into a best effort slice and see how it does. The best effort slice will run alongside other slices in the network. If there's spare bandwidth, then we give it to apps in the best effort slice. So we drop this app in a best effort slice, and then we observe it for a short duration. If it ends up meeting the SLAs in this duration, we guess that there might be available capacity. This could work sometimes, but there could also be scenarios where the bandwidth available for a best effort, there is bandwidth available for a best effort, there's no bandwidth available in the best effort slice, but the app could be packed into an existing slice without any additional bandwidth. And so what we want to do is eliminate false negatives. So our approach instead is to estimate the distribution of bandwidth that's required for each slice over some predetermined contract duration. Now, one way to do this is to run thousands of microsimulations of Zypper over different channel traces to see how much bandwidth is required. But this is extremely expensive. What we really need are the bandwidth statistics, not the resource schedules. So we're going to approximate those statistics using a family of deep neural networks, 1 DNN for each slice. So let's say we have our incoming app, and then we also consider the other admitted apps. So for each slice, we run the DNN to obtain a distribution of the bandwidth required for each slice. And then we combine these distributions to compute a composite distribution of the total bandwidth required to serve all apps, including the incoming one. Operators can then use this metric downstream with the policy. Before discussing the results, I want to run through some highlights of our implementation. We deployed Zypper on a production-grade testbed, and this is what the hardware looked like. This is a real testbed working with real phones, and we're able to dynamically adjust the bandwidth for real mobile applications. In software, we wanted to implement Zypper in the least invasive way possible. So we started with standard software stacks for the core and for the RAN, Zypper interfaces with the RAN, and then we instrumented telemetry to monitor various stats from the RAN that Zypper uses internally. And then we added a control hook to update the RAN bandwidth based on what Zypper allocates. Now, one limitation of this implementation is that the Altran software that we use for slicing supports just 1 slice. To evaluate Zypper end-to-end, we ran a simple experiment on this testbed involving a OnePlus phone doing a video download at 17 megabits per second. That was a throughput SLA. We move the phone around in an indoor environment, and we indicate the stationary period of time in yellow. This time series chart shows the SNR measured over the course of this experiment. And this is the throughput that Zypper delivers over the course of the experiment. Notice that it complies well with the SLA. And here's the bandwidth that Zypper allocates to the slice. Notice that the bandwidth required is greater when the measured channel is lower. As I said, with a production-grade testbed, we were limited to just 1 slice. And it's also hard to evaluate different baselines in a controlled setting. So we built a trace-driven emulation framework consisting of several apps shown in this table here. We use a simple metric to evaluate performance. We define a penalty that quantifies by how much the achieved throughput or latency deviates from the SLA. This is how it looks for throughput. I'm going to walk through one experiment that summarizes the key results. We evaluate Zypper against 4 other baselines. First, an Oracle solution that uses the ground truth channel trace instead of the channel forecaster. Second, NVS is a slice-level service assurance method. QoS is a priority-based scheduler that doesn't use slicing. Single slice schedules all apps within one slice without any priorities. And then we look at the penalty, how the penalty varies as we increase the load or the number of apps. For these experiments, we disable admission control. Notice that Zypper does really well up to 150 apps, incurring a similar penalty to that of the Oracle solution. QoS and NVS do a little bit better than single slice on service assurance, as we expect, but because they do some degree of prioritization. Now let's evaluate the resource availability estimator in the context of an admission control policy. Recall that our primitive returns a distribution of bandwidths required to service an incoming app, along with all existing apps. To evaluate this primitive, we consider a simple admission control policy that admits apps in a first-come, first-served order, as long as the 95th percentile bandwidth is less than the total available bandwidth. We compare against a baseline that conditionally admits apps to a best effort slice to probe resource availability, as we discussed before. We're going to look at the admit rate as we vary the number of apps. Initially, at 100 apps, both policies have similar admit rates since the network isn't oversubscribed. Now, as we add more apps, notice that the admit rate drops. But the DNN forecaster that Zypper uses is able to maintain a higher admit rate as more apps try to join. This is because it's able to differentiate between different traffic types because we maintain a family of DNNs. For instance, the DNN can infer that a voice app could still achieve its light target throughput and latency because the MAX scheduler can accommodate it without degrading the SLAs of other apps and without adding more bandwidth. So to summarize, Zypper is the first 5G RAN slicing system for app-level service assurance. In addition to building the bandwidth optimizer, we propose a primitive that can be used with Zypper to forecast resource availability. And finally, we evaluated and implemented Zypper on a production-grade testbed and evaluated it on real workloads. Thanks, and I'm happy to take questions.